let's talk about the standard deviation and how we can use it with the normal model as a ruler. Well, the first thing we need to know is the standard deviation helps us standardize values. What do we mean by that? Well, let's say we're taking two tests. We take a math test, and on the math test, our observation, our y value, is an 80. On the physics test, we had an observation of a 60. Now, which test did we do better on? Well, you might say the math test, but let's say on the math test, the average on the math test was a 70, or the average on the physics test was a 60. Now, if you'll notice right here, on the math test, we scored higher than average. But what if it was different? What if on the math test, we scored lower than average? Y bar math means the average of the math test, and we scored an 80, so now we're below average, but we're still average for the physics test. How about if both tests, we scored the average? Now, in this instance, we scored an 80 on the math test, and the math test was an 80 average. The physics test, we scored a 60, and the physics test had a 60 average. There has to be some way to equally compare these and to standardize these values, and that's what we'll be covering in this lecture. We can think about things like height. What if you are 75 inches tall and male? Well, a good way to compare you would be to compare you to the average male, who is 69 inches tall, and then to think about how the distribution of males have their height spread out. 3 inches is the spread of height, and we can draw a normal model down here. Where at the center of the normal model, we put 69 inches, and then we start going up standard deviations. What this would mean is every mark on the curve is 1 standard deviation above the mean. So a male who's 75 inches tall would be right here. It'd be 3 standard deviations above the mean. Do a little color coding here to help out, where the standard deviation is 3, and then the mean is at the center of the curve, which is right there. So an observation of 75 inches is 2 standard deviations above the mean because you are 6 inches taller, and a standard deviation is 3. And this is what we're doing in this chapter. We're trying to figure out when is something unusual. And that's kind of unusual. You know what's really unusual? The tallest people in the world, Sultan and Yao. So Yao right here is, she is 7 feet 8 inches, 92 inches, and Sultan is 8'3", which is 99 inches tall. But who is more unusual? Now, it's pretty easy to say if you have a male who's 6 feet tall and a female who's 6 feet tall, then probably you'd think, well, the male's more unusual because males are typically taller on average. So with that in mind, Yao's a little bit shorter, but hey, you know, maybe this is really tall for a female. Well, we'll find out here in a moment because we'll need to compare them to their respective distributions to figure out how unusual they are. So this is what we're doing in this chapter. We are comparing things on an equal playing field. The standard deviation tells us the spread of the data, and then we can compare things to the mean in terms of the standard deviation on how far they are away. To do this, we can run the formula observation, which is whatever we see in the data, minus the mean, which gives us a distance divided by the standard deviation. So think about what this formula is asking. It's saying, how far away are these values, and what is that in terms of standard deviations? That is a z-score. A z-score tells you how many standard deviations something is away from the mean. Our individual who is 75 inches tall and has a mean for their distribution of 69 and a standard deviation of 3 has a z-score of 2. They are 2 standard deviations above the mean. Going back to the data right here, I often write below this the z-scores so it's easier to tell. Now, if you notice, not everything would fall on a whole number z-score. How about somebody who's 70 inches tall? Try to solve it right now. 70 inches minus 69 divided by 3, you get 0.33 repeating. And that means this individual, we'll circle them here and we'll draw a line, would be right there at a z-score of 0.33. Notice how they are barely above the mean. Someone who is at the mean has a z-score of 0 because they have no distance from the mean. If you are 66 inches tall, you would have a z-score of -1 because you are 1 standard deviation below the mean for this distribution. It's important to note that we can describe the distribution as normally distributed, that's what the capital N means, with a mean of 69 inches and a standard deviation of 3. The first value in this is the mean of 69, and the second value is the standard deviation of 3. So when you write normally distributed, you're trying to describe the shape of the curve, and the shape being normal is what the capital N means right there. And so normally distributed, and then the mean is the first number, goes at the center, and then the standard deviation is 3, which is how you go up and down 3 standard deviations. Now, it's important to know that there are more than 3 standard deviations that you can go out. It's just we see pretty much most of the data within plus or minus 3 standard deviations. 99.7, as we'll hear later, 99.7% of the observations are within plus or minus 3 standard deviations on the normal curve. So aside from outliers, so really outliers would be beyond here, that's where you would see extreme things. Outside of 3 standard deviations are the outliers. The more common data is within -3 and +3, but just because something is -2.99 doesn't mean it's unusual. It's just by a lot of classifications not quite an outlier. It's still pretty unusual, and you could say it's almost an outlier. So we have the formula right here, and we're going to figure out who is more unusual in terms of z-score. Let's go ahead and plug in Sultan's height and the mean for his distribution, which is 69. That means he is 30 inches taller than average. We divide by 3, we get a z-score of 10. Now Yao is going to be a height of 92 inches. We minus off the mean for her to find out how far she is away from the mean, and then we divide by the standard deviation, and we get a distance of 28.5 divided by 2.5, which is a z-score of 11.4. So the z-score of 11.4 means Yao is 11.4 standard deviations above the mean, which is super duper unusual. This is extremely unusual and very unlikely to occur by random chance. Just take a look at the curve over there, and you'll notice she is basically completely off the curve. We would not expect individuals over there. Most individuals would be within plus or minus 3 standard deviations. That's where we more commonly see individuals. So remember, we can compare things with context using z-scores. A z-score lets you know how many standard deviations something is above or below the mean. But let's say your friend tells you their z-score. We can rework the z-score formula, and this is a good one to write down, as the following. We can say that the mean plus the z-score times the standard deviation is equal to the observation. And this is what you're doing when you tell someone a z-score. If your friend says, I have a z-score for my height of 3 and I'm male, well, they just told you their z-score is 3. We know the mean for men is 69 inches, and the standard deviation is 3. Plugging in the numbers, 69 plus 3 times 3 is equal to 78. And if we go back and look at our data, we can see the answer. They would be 78 inches tall. They'd be over here at a z-score of 3. Drawing the curve can be a big help too to let us know where a z-score would be and what the observation would be. So this is a reworking of the formula right here to solve for the observation. Also, I use the population notation. So please note small differences right here. Let's highlight what each of these is. A z-score is how many standard deviations an observation is above or below the mean. An observation y is an observed value, like somebody's height is what we see. The sample mean of y bar is the sample mean of data y. The standard deviation is the spread of the variable we're measuring. This is the population mean, which is analogous to the sample mean. It just depends if you're talking about population data or sample data. The z-score right here is the same previously. It's how many standard deviations something is above or below the mean. And the standard deviation right here is for the population data, which is analogous to S for sample standard deviation. So we have population standard deviation and sample standard deviation. It just depends if we've collected data from a sample or if we're speaking for a population on which formula we're using. We now get to the idea of shifting and scaling data. When you shift and scale data, you are moving either the center of the data or changing the spread of the data. So how does shifting data look? Well, if you have a number line and you shift your data, shifting the data would move the center of it left and right. It would reposition where the top modality peak of the data is. Where when you scale data, you change the spread of it, which is going to change the standard deviation. So think about what changing the center would change. It would change the mean, it would change the median. It actually also changes things like Q1 and Q3 because those are just positions. It's like the mean's a position and the median's a position. Now the scaling would change the spread, which would change things like range, would change things like standard deviation and IQR. So it would not change, in some instances, the shape of the data, as we'll see, but shifting changes the center, and it also changes other metrics like Q1 and Q3, and also, I guess you could say, the min and the max. Because think, if you're moving this data right here across this number line, you're going to change what the lowest value is, and you're also changing the center. Where this is going to change the range of the data, the distance of the min to the max, it's going to change how spread out it is with standard deviation, and it's going to change the IQR. So now, let's go ahead and look at a classic way we use this in statistics. In statistics, we standardize data a lot of times by turning it into z-scores. Z-scores means we shift it to a center of 0, and we rescale it to a standard deviation of 1. So you could have data that looks the following way. It could be test scores that go from 40 to 100 that are normally distributed. And then when you turn them into z-scores, you're going to have the average at 0. And if it's normally distributed, it'll generally be between positive and negative 3. You don't change the shape of the data, but take a look at the rescaling of it. The rescaling of it is going to be that it's much tighter than before. If we go out 3 standard deviations, a standard deviation is now 1, where previously a standard deviation was closer to 10. The shifting of the data speaks to the mean being moved, where the mean might have been around 70, and now the mean is at 0 because it's a z-score, and the z-score of 0 represents someone at the mean. Once again, turning it to z-scores does not change the shape of the data. We know a lot about shifting and scaling, though, because we do this for things like temperature with Fahrenheit and Celsius. If you have a temperature in Fahrenheit, you could run it through a formula and turn it into Celsius. This wouldn't make it any hotter or colder during the day, it would just change the context. So the z-score formula, which can turn something into a z-score, is doing the same sort of thing. Observation minus mean over standard deviation. Plug in any value like the maximum value and you will get the z-score. And if you do the same thing for Celsius and use the mean and the standard deviation, you'll get the same z-score because it's still the same unusual nature. So how about this normal model that we've been talking about? The unimodal symmetric curve. Unimodal, one peak, symmetric, it can be folded over on top of itself like that. We use this a lot of times to talk about if something is unusual. Something is unusual when it is more than 3 standard deviations above or below the mean. And so now, let's make sure we can give it a z-score. Z-scores are going to allow us to have context for our data when we draw the normal curve. Here's the normal curve right here. We can give some estimates of z-scores because most data is within positive or negative 3 standard deviations. So if you put the mean at the center of the data and go out about +3 standard deviations, you can get a good guesstimate of what the standard deviation is. I think it's a little more than 2. And then you would go down the -3 standard deviations to -1, -2, -3, +1, +2, and +3. Always draw out your z-scores and the context for your data when drawing your normal curve. Very clearly, as we stated, Yao is well beyond 3 standard deviations above the mean. She is extremely unusual and unlikely by random chance. So we can take and run the z-score again, make sure to know your notation, that the observation minus the mean divided by the standard deviation is a z-score. Once again, a z-score is going to tell us how many standard deviations something is away from the mean in the positive or negative sense. We talk about things being normally distributed with a mean, the first value, and a standard deviation, the second value. So try to draw this out right now. If I say something is normally distributed with a mean of, let's say, 10 and a standard deviation of 2, you should be able to draw a normal curve, and at the center put 10 and go up 3 standard deviations, down 3 standard deviations, and write the numbers using the standard deviation as the distance between them. Notice, and I'll stop filling out the curve there, that the standard deviation is the metric by how much you go up each time, and the center of the curve is going to be right there at the center of the curve, which is the population mean. Now we also have the standard normal curve. The standard normal curve is a very special one with a mean of 0 and a standard deviation of 1. It's called the standard normal curve because everything on it is a z-score. So you could take that same data we just did, normally distributed with a mean of 10, a standard deviation of 2, draw it out, and then below it, you could put the z-score. I do this a lot of times to solve problems because we might need to know the z-score. Like imagine if I asked you, for this data, what is the z-score of 1.5? Well, you can take the z-score right here of 1.5, and you could go to the data and use the formula we said of mean plus z times sigma equals y. Plug in the values, and you get 10 plus 2 times 1.5 equals 13. And now when you look at it, you could have seen that right over here. That's where 1.5 is at the value of 13 for an observation. So knowing how to use this to your advantage is important because you can always write your standard normal below your curve. So there's the standard normal below there, so we can get a reference of what the z-score is for the data. Important rule in statistics. The important rule in statistics is the empirical rule, the 68, 95, 99.7 rule. And what does this rule mean? Well, it's the percent of data within 1, 2, and 3 standard deviations. So when we think about test scores on a test, what would we expect if the test had a mean of, let's say, 80 and a standard deviation of 6? You can put 80 here at the center, and look, we already have the standard normal curve right here. We've already written out our standard normal curve right there. And now we go up a standard deviation, another standard deviation, properly, 98. We go down. So what does this mean? Leave the last number right there. This means 68% of people would be expected to have a test score between 74 and 68. 95% of people would be expected to have a test score between 68 and 92. Going down one more standard deviation, we'd get to 62 right here. So we would have 99.7% of people would be expected to have a test score between 62 and 98. That would be the majority of the class right there would probably have test scores within those scores on the test. When is something unusual again? 3. Kind of. Because it's not like 2.9 is not unusual. Think about if you kept getting taller and taller and taller and taller and taller. It's not like when you go 3 standard deviations above the mean, you're unusual. You're just getting progressively more unusual. Also, as I'm getting older and older and older, I'm shrinking. So I'm not at one point going to become an outlier. I'll just become more unusual. So we do mention that it's 3, but do remember, once again, it's in the absolute sense that you could be an unusually low value, negative z-score, or unusually high value, positive z-score. But if something is 2.999, it's pretty unusual. If something is 3.01, it's the same amount of unusual, but technically beyond our threshold by which we say things are unusual. So 3 is usually our cutoff for an unusual point that we would call an outlier. But we want to make sure we're doing this with normal data. All these concepts I've talked about so far only apply if the data is unimodal, symmetric, normal. So how do we know that? Well, we can look at the data. Look at this data right here. What do you see? It's a monster man. Right to the high, left to the low, whatever way the monster man's tail goes. We got some outliers over here. We got right skew. So remember, positive right skew to the high. This would not be a time to use the empirical rule. So only use the empirical rule, the 68, 95, 99.7 rule, when the data looks like this. This is not a monster man right here because there's no skew to this. This is not skewed in either direction. The more normal it looks, the more we can use the empirical rule, and it should only be used for data when it's normal. There are other rules like the Chebyshev rule, which we don't cover here, but it can be used for all data. This is not the time to use the empirical rule with this data. But what are percentiles and how would we find them? Well, a percentile is just the percent of data below a certain point. So if you have this right here and you're at the middle of the curve, you're at the 50th percentile. So the median and the mean on a normal curve are the 50th percentile. We know other percentiles too on the curve, like the 25th percentile is Q1, the 75th percentile is Q3, and the 71st percentile would be somewhere over here because percentile means area below that point. It'd be above the mean and it'd be over there somewhere. That's about where the 71st percentile would be. because 71% of the data is below the 71st percentile. We'll have more exact ways of figuring this out here in a moment. But be careful with the empirical rule. Don't just divide things. If you have the empirical rule right here, and you take and you say 95 is between here and here, between -2 and 2, and 68 is between here and here, you can't just go between and say 81.5 is between here and here, as in this line and this line right here. I drew that one not so perfectly. You can't just draw right there like that because of the imbalance. If you take a look, there's more area here and more area here. So do not, with your empirical rule numbers, start dividing them in this fashion. There are ways to use them, but because these areas right here are not perfectly symmetric, you can't go between them, and this is not the way to do it with the empirical rule right here. What we can do is we can use things like the applet. We also have ways to break down the empirical rule even more. We're going to break down the empirical rule and look at the applet next. Let's bring up a new slide right here to show how to break down the empirical rule. And this leads to a lot of test questions. So we need to first draw a big empirical rule, and grab a sheet of paper and draw along with me right here. Draw a big empirical rule, big normal curve, and we'll put a 0, 1, 2, 3. And then we'll go here, -1, -2, -3. And then we'll go 68, within positive and -1. 95, within positive and -2. And then 99.7, within plus or minus 3 standard deviations. Now we do what I call the inside-outside trick. You take 100, and you minus 68, and you divide by 2. What we're doing is we're going between here. We're saying between here is 68. So what is outside of here? Well, outside of there is 32, and then one of these would be worth 16. And the way you know you've done this properly is when you draw these numbers, you can go across these arrows, you get 100%. So 16 plus 68 plus 16 is 100%. We do the same thing for 95. We subtract it from 100, divide by 2. Disappear for a moment. And then we get 2.5 on either side. We do the same thing for 99.7. We subtract it from 100. We divide by 2. And we get 0.15, 0.15. That's below -3 and above +3. So what have we found? We've found the area outside of these regions, and this can be very important to use, and I highly suggest writing it down. The next thing we probably want to do is start writing down the numbers in the cumulative sense. Starting at the bottom, we get 0.15, and then we're going to go to the next one, 2.5. We go to the next one, 16%, and then this is a weird one because there's no number here. If we're at the middle, it's 50%. Now, when we get to the top, we have to subtract from 100 and get 84. And that's an 84. I don't want it to look like a 9 right there. 84%. And then 97.5, because 100 minus 2.5. And then 99.8. Write that a little bit nicer. 99.85. There we go. We didn't write percent. Oh, we wrote a few percentages. And so with this right here, that is the percentile we are at in the data if you look what is below it, as in at a z-score of 1, 84% of the data is below there. And you can add up or subtract from 100 to get that. Additionally, we can do the areas between these. And we would get between -2 and -3 is 2.35. Between -2 and -1 is 13.5. Between -1 and 0 is 34. Look at this, 34 between that, which almost is like 34 and 34 is 68. You can check your work right there. And then between 84 and 97.5 is 13.5. Notice how it's symmetric, 2.35. And we could even say above this is 0.15. That's not between -3 or +3 and +4. It's completely below there. So we might even draw an arrow pointing right there. Now, once again, try to write this out, try to practice this, because right here is a major study thing for the test. If you know how to write this out, if you understand what these numbers are and what they mean, you'll be good for the test. So we also can solve this using the applets. So take a look at this question right here. What do we have? You'll notice that this is about SAT scores. A z-score of 1.8 means the person was 1.8 standard deviations above the mean, which you can tell, looking at this, they would be right over here. That's where a z of 1.8 is. And that is a score, an observation of 680. Well, we have applets to help us out with this here, and we can put the numbers into the applet, and we can see what percentile they're at. Using the normal model here, a normal model with a mean of 0 and a standard deviation of 1, right there, you can input the observation of 1.8 and find out they are in the 96.41 percentile. Or you can put in the actual values of the data, the mean and the standard deviation, seen right here, and you can put in the observation and get the same exact answer. We can also check the empirical rule with this right here to say, what is the percent of area? Find the percent of area using the values between -1 and 1, and we get 68, 95, 99.7. Notice how it's more exact. This is because the applet gives you more exact numbers when solving these sorts of questions. Let's go ahead and take a look at the applet here on the main screen. Let's point out what we already have on the applet. We have that we are looking at body temperatures. A mean body temperature is 98.2, and the standard deviation of body temperatures is 0.7, telling us how spread out they are. We're looking at the middle 50% of body temperatures, which range from 97.73 to 98.67. We are currently finding the IQR. Subtract these numbers and get about 0.94, and you have found the range of the middle 50%. What if someone told you their body temperature was in the top 10% of body temperatures? Well, then we would simply go to above right here and put in 10%, and the top 10% of body temperatures is 99.1. What if someone told you they're at the 80th percentile? Well, percentile means data below. So now the 80th percentile of body temperatures is 98.79. Now be careful because questions can be phrased differently. Percentile means percent of people below you, where you can state things like the top 5%. So the top 5% would also be the 95th percentile, which can be viewed. So with this in mind, you can tell where percentiles are at. Percentiles are the percent of data at or below an observation, where we can also talk about the top percent, but then we'd have to turn it into a percentile, like this is the 95th percentile, or the top 5% of the data. Let's change this over to find the percent using an X. So we might ask, what percent of people have body temperatures below 99 degrees? And there we go, 87% of people have body temperatures below 99 degrees. What about percent of people who have body temperatures between 98 and 99? And it would be 49%. So the applet can be a huge help and get us direct answers to many questions. Feel free to use it and know how to use it. We won't have you use it on tests for our class, but you should know how to look at it and figure out from pictures what would we ask you on a test. So know how to use it, but you won't use it on the test. You might see pictures on the test and know how to derive answers from pictures. So we were just talking about those body temperature examples. You can go ahead and input data like that into the applet. Here is the 25th percentile of body temperatures on a curve with a mean of 98.2, because that's where the center of it is at, and a standard deviation of 0.7, because that's the spread of the curve. Go to the applet right here and enter in the mean of 98.2 and the standard deviation of 0.7. Then we can ask for the 25th percentile. Go ahead and try to solve this right here. This will let us know our answer. And we just did it previously, but check out the applet right there. See if you can solve for the 25th percentile. But how do we know if data is normal? Normal data can be checked by just looking at it. But what if we had a plot that tells us the probability? It's normal. A normal probability plot lets us analyze the probability our data is normal. How will it do that? Well, it's going to let us know if it's unimodal symmetric, which is the normal. And we can compare it to the histogram and see what's going on. Here's the histogram of our data, two unusual points down there, and the normal probability plot right here, normal probability plot, is over on the right. Now, if the normal probability plot follows the normal, it'll follow a line. Now, that doesn't mean it's linear, it just means it follows what we would expect given it's normal. If it's not normal, then it's not going to follow the line. notice how there's deviations at these portions, and also the histogram is more skewed with outliers. So the big note to have right here is a normal probability plot is going to tell us whether or not we have reason to believe our data is normal or not. So you look at the data and you ask, does it mostly follow that line down the center? And there's these kind of meh lines, which are kind of, is it perfect? No. But for the most part, the data follows the normal and it looks kind of normal. Remember, it doesn't have to be perfect. It just has to mostly follow the normal. And if it does, well then, it's mostly normal. We do have an additional test called a goodness of fit test. And it goes to a big idea in statistics of the null and alternative hypothesis. So the null hypothesis would be that the data is a good fit. Right here, good fit. The alternative hypothesis is that it's not a good fit or bad fit. The null is what we believe until there's evidence for the alternative. So if we were to see data that followed the null, we would continue to believe it, and we'd believe the curve is a good fit. If our data doesn't follow the null, we'll have evidence it's a bad fit. We'll see some examples of this here in a moment. An important thing we will use to decide this is a p-value. A p-value tells us what is likely given the null is true, if our results were. So when we get the p-value, we'll ask, is what we saw here likely given the null is true? Let's look at some examples. In the first example right here, you'll notice the p-value is higher. And by higher, high p-values are greater than 0.05, greater than or equal to technically. So this is a not statistically significant p-value, a p-value that is likely by random chance, not statistically significant. And what we're saying here is that what we saw with this data is likely given the null is true. So we believe that if this is, our data comes from the normal, what we saw here is something we would expect to see. Take a look. It follows the line, the curve looks to fit over it. So statistically speaking, one might say, I do not reject the null hypothesis. I fail to reject the null. I do not have evidence it's not normal. But now, how could we respond if it wasn't normal? Take a look right here. Here you see more outliers, things that deviate away more. You see a little bit of a skew. And now we would say we reject the null. The p-value is low. I reject the null. I reject that it's a good fit. I have evidence it's a bad fit. And when do we reject the null? I like to say when the p-value is low, reject the null. When the p-value is high, just let it fly. Take a look. P-value low, reject the null. I reject this null. I reject that it's a good fit. I have evidence it's a bad fit. Now that's what I believe. I don't think the normal curve is a good fit. I have evidence that this is not normal data. In the previous one, I don't reject the null because my p-value is high. I just let it fly. I let the null fly. So since the p-value is high, I let the null fly. I do not reject the null. I continue to believe. Now, I'm not saying I know the normal curve is the right curve, but I think it's a good fit. I don't have evidence it's a bad fit. So I do not have evidence it's a bad fit. And with this in mind right here, we'll see more p-values coming up later. So make sure to review these topics and know how to check if things are normal and know the empirical rule and know z-scores. Good luck.